don't know everything.
What? So I learned. So Quinn asked a question the other day. I think I told you guys this. Visible light can't go through this wall, right? If you're outside this with a flashlight, I wouldn't know. Couldn't even see you, right? But cell phones, we talked about this, use microwaves. That can go through the wall to the cell tower, to the satellite, to the cell tower, to your cell phone, or whoever around Texas, whatever. What's that?
It's gotta find some other.
It goes right through this wall.
Actually.
Yes. So microwaves can go through walls. But if we were to go, I don't know, 30 feet underground, probably wouldn't work too well. Would we all agree?
Yeah.
Okay. Or if you ever been in an elevator,
Yeah.
sometimes try and use it. That doesn't work. It's a metal box. Metals don't play nice with radiation. So I didn't know. Quinn said, well, how come if microwaves are these big waves and gamma waves are way down here, they're little, right? Little wavelengths. So again, here's your microwaves, and your gamma waves would be like this. Okay? So the magnitude, the intensity could be the same, but the size of the wavelength from here to here is very small. Gamma and cosmic rays, actually the wavelength can be smaller than atoms. Whereas microwaves and radio waves, like she said, football fold or whatever she said. So those are really big. So his question was, if visible is in between here, right? We have these really big wavelengths, microwave, radio waves, they can go through walls. Gamma rays, cosmic rays, they can go through walls. But why visible is in between? Why can't that? That's a logical question, right? So why can something big and something small, but something in the middle can't? And I found an answer online from this physics website, and it's the Goldilocks thing. What's Goldilocks all about?
Just right.
Porridge, right.
Yeah,
But
right.
just right is what it's about. Okay, not too hot, not too cold, just right. So this is kind of cool. The analogy they use, and I'll read this. And the reason I'm spending time talking about it, because I think this is really cool and fairly appropriate for real life. You know, some stuff we talk about, it's really hard to directly relate to real life. This one you can relate directly. So there's 5 things that affect radiation when it encounters a barrier like a wall. Here's the 5 things. The wavelength of the radiation, the intensity. Now intensity would be the amplitude of the wave. So if it's very intense or not very intense. So think of like light from the sun is way more intense than a flashlight. Would we agree? Okay. Or you could have like some of those work lights. Like I have a halogen work light. It gets crazy hot and it's super bright. That's way more intense than like my cell phone flashlight. So do we agree on that? So that's what it means by intensity. Chemical composition, what the wall's made of. All right, that's obviously important. Is it made of carbon? Is it made of steel? Is it concrete? You know, the chemical composition. Then the physical microstructure, what does that mean? Not just what it's made of, but how the atoms are arranged, how it's put together. And then 5, the thickness. If I had a concrete wall that was paper thin, we might be able to see light through it. Would we agree? Like if we hold a piece of paper up to a window, we can see light coming through. Okay, so the thickness plays a role. So those are the 5 things. So the question again is, why can microwaves, and this was exactly the question on the site, which not everything online is true, but this seems legit. It's a physics website, physLink.com. Physics and Astronomy Online. It's, you know what, I don't think it is, but they answer, so taking what I know, makes sense, and I'm going to say it's correct. So here's the example. Ready? Imagine an ant and an elephant standing next to each other. All right? The ant doesn't know the elephant is there because it's too big, and the elephant doesn't know the ant is there because it's too small. Do you agree with that?
What? No.
Yesterday, someone had a problem with well, if I'm an ant, I'm going to know there's an elephant.
There's an elephant. Yeah.
No, not necessarily. Elephants are enormous compared to the ant. So imagine you're an ant and you're right next to this gigantic elephant. Yeah, you just see this gray wall next to you if the elephant's not moving. The analogy is we are ants and the earth is the elephant, right? So if we didn't know anything about anything, we just kind of existed and met our basic needs, you know, we need to eat, sleep, and whatever. Okay, so we're not, imagine we don't have much of a brain. We would have no concept that the planet is what we're on. We would just see our immediate environment and think that's our whole world. Fair to assume if you can put your mind in that example, right? Kids are kind of that way. They don't realize there's more, like little kids. Like my daughter doesn't understand the concept, you know, like if you were to walk in the same direction, you would eventually come back in the same spot, which is why the earth is not flat.
Water.
What?
You can't walk on water.
Hey, so,
I'll talk to you later.
yeah, this is interesting. You want to hang out for a second?
Yeah.
Why microwaves can travel through the wall, but visible light can't, and gamma rays can. Now you may know, I didn't really know, so I looked it up, and this is cool. So,
Let's see what they say.
yeah, so it's an astronomy and physics website, and I think it sounds right to me. All right, so here we go. Electromagnetic waves interact with matter in a similar way on their own size and scale and time. The reason why visible light can't travel through walls as easily as gamma or radio waves is because to visible light, there's something there on a similar scale of length and time in gamma rays, time and frequency, I'm sorry. Gamma rays are too small and fast to interact with the wall, and the radio waves are too large and too slow to interact with. The gamma rays just pass through the spaces between and within atoms and molecules. They're small enough to do that. If your walls were made of pure lead, they'd have a little more trouble. The radio waves, on the other hand, are large enough to ignore the walls because they're too thin. So the analogy that I can explain that is if you hold a flashlight up to your hand or up to a piece of paper, well, some of the light transmit through here.
Yeah.
So imagine to a radio wave, this is a wall. So radio waves can go through it because it's so small compared to the massive wavelengths. That's what they mean by the ant and the elephant in the Goldilocks thing, is walls are just the right size and thickness to affect the light waves of visible light. Gamma is so small, it goes through it, and radio is so big, it kind of ignores it, kind of like a flashlight would with a piece of paper. Because again, this is like the wall in relation to big radio and microwaves. What do you think?
Yeah, I think that's good.
Yeah.
Like I add with the gamma, a gamma wave's come along and comes up to a wall, and to the gamma wave, the wall just looks like a molecule here and a molecule here and a molecule here, and it just goes whoop, 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 right between them.
Right.
They're just so far apart on the scale of how small.
Kind of like
the
if I was a gamma ray, these guys would be particles in a wall.
Yeah,
I could
you
just run right through.
zigzag right
Yeah,
through them.
yeah.
You'd be like, no problem.
That makes sense.
Yeah, I mean, I like to think of it that way.
Yeah.
That's good.
Yeah. Yeah, no, I thought it was a great example of trying to visualize. So again, like if this is the wall, the radio is so big, it'll go through it, which is why cell phones work in here, but I can't shine a light through the wall.
Yeah.
But
That's good.
yeah, and whatever. Yeah, we can. How about period 5? You want to talk?
Yeah, I just had a question if you can cover something for me tomorrow.
Oh, what
So-
period?
7th.
7th
7th is I think you're prepping tomorrow.
8th is my prep. I have forensics.
Oh, is that what it is?
Yeah.
That's even better.
Okay. Yeah, I can do 8th.
Yeah, I have this small group general physics.
Okay.
I'm trying to get this bridge project thing done down there, and I want to help them for the second half of the day. So.
Yeah, I can do 8th.
Okay.
Yeah.
All right. I'll give them something.
Right? We have lab today? Yeah.
All right. Good.
All right.
Thanks.
Yeah. So I thought that was cool. Kind of cool, right?
Yeah,
Not as
that's
excited
cool.
as me. That is cool. Now you know how these things work and why it works. Okay. But if this wall is made of lead, you know, it might not work so well for the gamma. So I thought that was really cool. All right. Now nuclear chemistry. Here we go. Why is it unstable again? The nucleus. What did we write yesterday? Ratio of what? Neutron to proton, right. So write this down. Stable nuclei, a 1-to-1 neutron to proton ratio. Proton. Yeah. That's stable. Unstable nuclei, we'll say 2-to-1 neutron. Now, there's a lot of room there between 1-to-1 and 2-to-1. I'm just trying to give you a very concrete example there. So, for example, if you have carbon 12 over 6, it has 6 protons, subtract 6 neutrons, so that's 1 to 1. But if you have carbon 14, which is radioactive, it has 6 protons and 8 neutrons. So it would be 8 to 6, which reduces down to 4 to 3, and you could figure out, you could divide that by 3, 4 divided by 3, whatever that is, right? So you could reduce it to make sense here. It's not 1 to 1. The point is, the further away from 1 to 1, the more unstable, which means more radioactive. So this is a radioactive element. It gives off radiation from the nucleus because the nucleus is unstable. When it gives off radiation, what it's doing is it's trying to alleviate the ratio problem and get back to 1 to 1. So I actually want to write some things down before I show you the video. It's going to make more sense if you do that. But this is what nuclear chemistry is all about and radioactivity is all about. And now the cool thing about radioactivity is when carbon 14 emits radiation, it'll turn into a completely different element. And that's the cool thing about nuclear chem. So it's like when you study chemistry, whether it's in school or for a job, and you're the whole realm of chemistry, like 90% of it is chemical changes involving electrons. And then the little 10% is this, nuclear chem. It's completely separate because it's turning into a different element. You're dealing with the nucleus. It's a totally different branch of chemistry. It doesn't follow any of the rules of conservation of mass and energy. No, throw all that out the window. All right, it doesn't follow those rules because you're changing the nucleus. All right, you're changing the mass, you're changing the protons, so you're messing with those laws. So hopefully that makes some sense. That's the basic thing we need to know. So moving forward, it's all about the ratio and what makes a nucleus stable or unstable. So let's write a couple things down before we watch the video. Okay, so radioactivity is the process of a radioisotope. Radioisotope, parentheses here, is all that means is a radioactive atom. The term radioisotope just means it's an element, an isotope that emits radiation. That's what that means. So a radioisotope, a radioactive atom, like carbon-14, that's just one example. Process of a radioisotope, radioactive element, or atom, emitting radiation. And that's alpha, beta, positron, or gamma. Those are the 4 types of radiation the atom will emit. Now remember, it comes from, right, I'll label that, from the nucleus. From the nucleus. So that's what radioactivity is. Radiation, gotta make sure we understand the terms here. The particles or waves emitted from a radioactive nucleus, which is an unstable nucleus. So there's this thing called the belt of stability. I'll show you that again in a minute. That's kind of how we know how radioactive something is. So what is radioactivity? It's when a radioactive element emits radiation. Well, what's radiation? It's these little particles, tiny particles, alpha, beta, gamma, positron, gamma is the wave, that are emitted from the nucleus. Questions? Sometimes I get going and I'm going too fast. Okay. Hopefully you guys were good there. Why does radioactivity happen? Why are certain things radioactive? Why are they emitting radiation? So why emit radiation. Why do these nuclei emit radiation? What are they trying to do? I said it yesterday. Become stable. So, an unstable nucleus, parentheses, radioactive. So something that is said to be radioactive. So radioactive material. If something is radioactive, that just means the nucleus of those atoms, they're unstable. The nucleus can't hold itself together, so it starts spitting stuff out. An unstable nucleus emits radiation in an attempt, to become more stable. And the analogy I use is if you get food poisoning, let's say, and your stomach's all messed up, sometimes you throw up. When we throw up, that's our radiation. That's the analogy. If we have a very unsettled stomach, okay, we feel really sick, sometimes your body says we got to get this stuff out, so we throw up, puke, whatever you want to call it. That's our alpha, beta, gamma positron. Hopefully, we feel better at some point afterwards, right? We become more stable. We got rid of the bad stuff. So the unstable nucleus is emitting radiation, trying to level out that ratio, neutron to proton, to try and become more stable. You guys ever hear half-life, the term half-life? I've said it. That's what's happening here. When things go through half-lives, this is what they're doing. And eventually they go through enough half-lives, they do become stable. Okay. One element over there that's radioactive. Uranium. Uranium takes like 4.5 billion years to become stable. So it gives off radiation for 4.5 billion years, then it's stable. It takes a long time. Some elements can become stable after seconds. Go to table N, please. Table N. I'll show you what I'm talking about. Then we'll watch it. Okay. What's table N say? Radioisotopes. All of those isotopes are radioactive. Find uranium-238 all the way at the bottom. See the half-life? Should be 4.5 times 10 to the 9th years. Or something very close to that. Yes? 4.7?
4.7.
Oh, 4. Yeah. Times 10 to the 9th. Yeah. Look at carbon. 14. 5,730? 5,715?
Yeah.
See, they changed that. The first, long time ago when I first started teaching, it was 5,730. Now it's 5,715. So it takes 5,700 years for carbon-14 to do this and become stable. Uranium takes way longer. So you can see some of them are in seconds, years, days. All right. Now the column next to it has little pictures, little symbols. What do you think that represents? The decay mode, right? That's what it says. But what do you think the symbols? What are they? Yeah, that's the radiation. If you see a B minus, that's beta. You see the thing looks like a fish or an A, that's alpha. A B plus is positron. They don't put gamma on there, but almost all of them give off gamma with those particles. So that's how you know what type of radiation is getting ejected out of the nucleus. All right, that chart's very useful. Okay. One last thing in the video. This process here, when it emits this, is called natural decay. There's three names: natural decay, radioactive decay, natural transmutation. Natural decay, radioactive decay, natural transmutation. That's what this, right here, this star, that's what this is called. When an unstable nucleus, so if I had a radioactive sample just sitting on my desk, it is just naturally emitting radiation. I don't have to do anything to it, it's just, it is, it's radioactive. These names, these titles, that's just describing the process. Decay means what? What does that mean to you guys? Break down. Good. What about this fun word? Transmutation. What does it sound like? Sounds like a mutation.
Sounds like biology.
Sounds like biology, right? This word means, and we're going to define it right now, one element turns into another element. And I'm going to show you this. And I know I keep delaying the video. I want to make sure I get all the important stuff down here today. What we're learning right now, discussing right now, is the most important part of nuclear. So, this word transmutation means one element turns into another element. So the analogy, here's the analogy. Let's say, who's it going to be? Reagan. Let's say Reagan's sick. She eats too much candy at Christmas time. She feels sick. So she throws up. She goes in the bathroom. She throws up. I'm laughing because this next part's weird. She goes in the bathroom, throws up. She opens the door. She turned into Sean. So, did you see her face? Like, come on. So, that's what transmutation is. Imagine you threw up and turned into a different person. That's what transmutation is. So, when carbon emits radiation, it turns into a different element. If we are all elements, every time we throw up, we turn into someone else. I go home, I throw up, I turn into Kara. Kara throws up, she turns into Vanessa. Vanessa throws up, turns into Dr. Peterson. Right? All right? So that's it's really weird. That's really weird. I understand that, but I'm giving you the analogy to kind of really hit it home that this is a very strange part of chemistry, and it happens naturally. These elements number 84 and higher. Right here. PO all the way up to 118. From 84 to 118, naturally, those isotopes on the chart do this. They're constantly emitting radiation, turning into a different element. Let me give you one example of this, and then I'll show what I can in the video. So here's an example. Let's look at table N. Let's look at the very first one. What's the very first isotope? AU 198, right? Okay, so everybody write this down in their notes. 198. Gold is 79. Now, gold is sick. Gold 198 is sick. It needs to throw up. It's unstable. It wants to become stable. So what it does is it emits radiation. Now you guys know to look up what type of radiation does it emit. What's the symbol? B minus, right? So what is that? Beta. So now if you don't know what that is, you got to go to table O. It's 0 over negative 180. So here's how we show it on paper. We draw an arrow. This arrow is showing AU is getting rid of something. So it's getting rid of this. That's your beta particle, which is B minus. Is the minus before or in front? Before or after? After. So it's B minus. There's a little tail on the B. So that's being emitted. So an atom of gold 198 is emitting a beta particle. But it transmutates. Again, Reagan throws up. This is going to be Sean over here. Now, who's Sean? If Reagan's gold, who's Sean? Now, this is very simple. It's just simple math. What number plus 0 equals 198? 198. That's the mass of this unknown element. Now, here's the tricky part. What number plus negative 1 equals 79? 80. 80 plus negative 1 is 79. So these equations actually do show conservation of mass. I know that's a little contradictory. So what element is number 80? Hg. This is called natural transmutation. When radioactive elements emit radiation, they turn into something brand new. So gold's no longer there; it's gone. It turned into hydrogen or mercury. Why does this make sense? Because you're changing the nucleus. You're changing the protons and the neutrons. You're changing it so it's actually gaining a proton, and it's turning into mercury. How does it gain a proton? It emits a beta. I know that sounds like magic, but that's how it works. Okay. So I kind of said a lot today. We didn't get to the video, I'm sorry, but we will watch it Friday. Tomorrow's a quiz, don't forget. You do have a worksheet for homework, but I'll make it due Friday. All right, we'll make it due Friday. I'll just give it to you now so you have it. And this sheet is due Friday. Okay, so do your practice test or quiz for the quiz. Put the answers on the Google Classroom. Look at your review sheet. And that's it. Have a wonderful day.